Hello, and welcome to the Preparing for the AP Calculus exam webinar. Thank you so much for joining me. My name is Tracy Pratt, and I'm a math teacher in residence at NumWorks. Today's webinar is an advanced webinar, where we'll be taking a look at all of our calculus features the NumWorks calculator has to offer, as well as some advanced features that will help those who are preparing to take the AP Calculus exam. If this is your first time using NumWorks, I recommend that you start with our Getting Started with the NumWorks Graphing Calculator, or Graphing on the NumWorks Calculator webinars. Let's get started. The goals of our webinar today are getting the most out of our Grapher application, the power of our calculation application, solving derivative and integral equations, and looking at series and Euler's method as a sequence. To begin, we're going to open our Grapher application. Notice that I already have the function f of x equals x squared minus 5x plus 4 graphed. The first thing that I'm going to do is toggle on the derivative values of my function. To do this, I'm going to navigate to the three dots and press OK. Go down to values of the derivative and press OK to toggle this feature on, and go back. Let's take a look at the graph. Notice that I'm immediately in trace mode. Down at the bottom, you'll see the banner will include x, f of x, and f prime of x since I have toggled on the derivative values. For this function, I would like to see a little bit more of my graph. You can manually adjust the axes, which we'll do later, but for this function, I'll just zoom out a couple times by hitting my minus key. 1, 2, 3 times. And this gives me a pretty good view of my quadratic function. One feature that's really helpful for calculus is the ability to store the x values. I'm going to navigate to my first 0, and I'm going to store this as a. To store, I'll hit Shift X to the Y key to get my arrow, and then I'll use my Alpha A key to find this 0 as A and hit Execute. I'm going to do the same thing with my other x-intercept. Shift Store, and I'll store this as Alpha B. To store something other than the x value, simply press the toolbox to open up the options of the function. Here, you can do things like store the f of x value or the f prime of x value by again hitting that Shift Store button. I don't need to store this value, so I'm going to back out. Let's take a look at our calculus features available in the Find menu. I'm going to press OK. In the Find menu, down at the bottom, we'll have two calculus features. The first is a tangent line option. Press OK to open the tangent line. Now, as I scroll onto my function, you'll notice the bottom banner will include all things needed for the slope-intercept form of the tangent line at the given x values. I can jump to immediate values by using my number pad. So for instance, if I wanted to jump to the x value 2, I can do that. I can also jump to my stored values by pressing Alpha A to go to the first x-intercepts tangent line. Let's press OK to get out of the tangent line. I'm going to go back into my toolbox and back into Find to look at my other calculus option when I have one function graphed. That's going to be an integral. Press OK to find an integral. To use our integral, you can use your number pad to type in your bounds, or you can use the left and right arrows to scroll to those values. But I'll do the integral from 0 to the upper 0, Alpha B, and press Execute or OK to find the integral. The last thing that we'll look at is our calculus features available in the table. I'm going to press OK to get out of the integral and navigate up and over to the table and press OK. Because my value of the derivative has been toggled on, not only will we have an x column, an f of x column, but we will also have our f prime of x, which is our derivative values in table form. To hide this column, simply press OK and hide the derivative function to toggle that off. If you're interested in toggling that back on, from the f of x, you just simply press OK, and we can again toggle on the value of the derivative. I'm going to leave this off for now. The next thing that we're going to take a look at is how to create derivatives and integrals of our functions graph. Let's navigate up and over to the Expression tab and press OK. At the moment, I have my f of x function already stored. I'm going to leave my f of x function, and now I'm going to take a look at the graph of the derivative of f. To create the graph of the derivative of f, I want to make sure my highlight is on Add an Element, and then I'm going to press my toolbox. Within the toolbox menu, I can navigate down to the calculus section and grab the derivative of the function. So here I'm going to do ddx of f of x. To tell the calculator that I'm taking the derivative of f of x, I'm going to use my var key and go into the functions that I have stored and grab my f of x function. Now I need to input my argument x, and I'm going to make sure when I'm taking this derivative, I'm going to evaluate this at the x value x. This is going to take the derivative with respect to x and graph that derivative. Press execute. Just to show you this graph, I'm going to go down to plot the graph, and now we'll see not only my quadratic but my linear derivative. Going back to the expression tab, if I wanted to create a higher ordered derivative, I can simply edit my derivative and add an exponent onto my derivative. So for instance, if I wanted to look at the second derivative, I could square that derivative. And now what I'm doing is the second derivative with respect to x twice. Press OK, navigate down, and we'll see our constant second derivative. Let's navigate back and do one more expression that we can graph. I'm going to delete my derivative function. I'm going to use my toolbox to navigate down to add an integral of this function. I'll use the lower bound 0 and the upper bound x. And I want to change my bound of my integral to d of t. What I'm doing is creating a possible antiderivative, or looking at the accumulation function on f of x. To do this, I need to do this with respect to another letter, so I'll use alpha t here. Now when I navigate into my integral, I'll use my var key to grab my f of x, and then I'll use my x and t key, which, because my integral is now in terms of t, will default to the value t, and hit execute. Again, what I've just done is I've created a possible antiderivative, or the accumulation function from 0 to x. Let's go down to plot the graph to see this cubic antiderivative. One thing worth noting is that now that I have two expressions graphed, I do have another calculus option in my Find menu. I'm going to use my toolbox and navigate down to Find. Now the very last option is the area between the two curves. We'll take a look at an example of this in a little bit, but know that this becomes available when you have two or more things graphed. Let's use some of our calculus features in our Grapher application to answer question 2 from the 2015 AP Calculus AB free response question. In this question, we have two functions, f of x and g of x, and they're showing us the graph of these two functions. We're letting R and S be the region enclosed by the two functions f and g shown in the figure below. Find the sum of the area of the region R and S. The first thing I'm going to do is I'm going to use my calculator to input my two functions in my Grapher application. Now that I have my two functions graphed, let's go down to plot the graph. Here, the auto zoom is showing me way too much of the graph. As we can see, I'm only really seeing a little bit of that first quadrant. So let's edit our axes. I'm going to navigate up and over to axes. And let's maybe start by making our axes equal. And then I'm going to use my plus to zoom in. Here I can also use my cursor to trace my function and see a little bit more of what I want to see. Zoom out just a little bit. This gives me a pretty good picture of my curve. You can also edit your axes individually. In your axes, you can input different values of x and y that you're interested in seeing. But I'm pretty comfortable with the graph that I've created so far. Now that I have a picture of my graph, question A says find the sum of the area of the regions R and S. I'm going to press my toolbox to open up my menu and navigate down to the Find option. Down at the bottom, I'll have my option of area between F and G and press OK. Now I can use my bounds. Because I'm finding the area between these curves, I want to find both R and S. So I'm going to start my lower bound at 0, and I'll write this down because they'll want to see the integral that I'm computing. So my lower bound here will be 0. And my upper bound will be from R through to S and all the way at the end of the S to 2. And hit execute. I'm going to write down the integral that I'm doing. I'm doing the absolute value of the two functions subtracted. That way I don't have to worry about the order of top and bottom of the two functions. And my calculated area. Let's move on to question B. Question B says, let the region S be the base of a solid whose cross-sections perpendicular to the x-axis are square. Find the volume of the solid. In order to find volume, I need to take the integral over the bounds of the area of the shape. In this case, my area is a square, and we're doing this with respect to the x-axis. So I'm going to find the integral over the bounds. We know that my area is going to be S, so the first thing I need to do is to find this lower bound here, and then to 2. So we'll call this lower bound B, and we'll call this upper bound, well, this upper bound is at the x value 2. So we're going to do B to 2, and the functions and the area that I'm creating is a square, so it's going to be the height between the two functions, and I'm going to square that value to create squares coming off of that shape. So we're going to find the height between, which is the top minus the bottom. Let's take a look at our graph to determine the top and the bottom. The top here is going to be my f of x function, so I'll do f of x minus g of x. And again, I'm going to square that because I'm creating a square. And the area here is area is equal to side squared. And we're taking this with respect to x, dx. The first thing I'm going to do is I'm going to navigate to that lower bound of where s starts and find and store that intersection for my b value. I'm going to shift store this as alpha b and hit execute. I'm also going to make sure I write this on my paper so that my grader knows that I know what b is. Now to compute this integral, I'm actually going to need to do this into my calculation app. So I'm going to press my home key and open up my calculation application. I'm going to use my toolbox and navigate down to my calculus section and grab my integral. I'm going to input my lower bounds. Because I stored that lower bound as b, I'll just do alpha b. My upper bound is 2. And then I will use parentheses and use my var key to grab my two functions, f of x minus g of x. Close that and make sure I square it so that I know that I'm finding the volume of squares, and hit execute. So my final volume is 1.283. Let's move on to question C. Question C says, let h be the vertical distance between graphs F and G in region S. Find the rate at which h is changing with respect to x when x is 1.8. So first, they're defining h as the vertical distance between F and G. So this is my h of x. I'm going to define h of x as that vertical distance between F minus G. They're asking us to find the rate at which h is changing with respect to x when x is 1.8. So they essentially want me to find h prime of 1.8. To do this, let's open back up our calculator. I'm going to use my toolbox to grab my rate of change, my derivative. Doing this with respect to x, and I'm doing this on h of x. So in my var key, my h is defined as f of x minus g of x. And again, I'm taking this derivative at 1.8. So my derivative value here is negative 3.812. The next application we want to make sure we have full grasp of is our calculation application. I'm going to press OK to enter my calculation application. The first thing I want to review is where we can find all of our calculus operations in our calculation application. I'm going to press my toolbox and navigate down to calculus and press OK. Here you can access your derivative at a value, your nth derivative at a value, your integral between two values, your sum, and your product. For an example, let's take a quick derivative. I'm going to press OK. I'm going to use my X and T key to create an expression. And then I'll input what value I want the derivative at. So for example, I can do 2 here. And this will give me my derivative at a specific value. Let's talk about how we can store functions directly from this screen, so that way if I wanted to do multiple calculus operations on the same function, I can quickly access those. The first thing I'm going to do is input the expression that I want to store as a function. So for example, I'll do the natural log of x squared plus 4. To store this as a function, I'm going to use my Shift X to the Y key and then my alpha keys to name the function. I'll name this one f of x. The great thing about NumWorks is we're not limited to the function names like f and g. We can also name them whatever we want. For example, let's create another quadratic. And I'm going to shift store this, and this time I'm going to name this a derivative function. So for example, I'll use my alpha d key followed by my alpha g key and name this the derivative of a g function. This is really helpful when what you're given is not the original function but a derivative function. Other useful things that we can do when naming functions is we can also use any independent variable that we want. For example, I'll do sine of t. To access t, I'll use alpha 6. And now I'm going to store this function, shift store, as alpha d x of t. This is really helpful for BC calculus if you want to do your parametric curves in terms of time, or if you're given a velocity curve in terms of time. Now that we have some functions stored, let's talk about doing our derivatives and integrals in terms of t and instead of x. Let's go into our toolbox and we're going to grab first the derivative d dx of a function. The default here is that the derivative is in terms of x. So if I'm doing a derivative where the argument or the independent variable is t, I need to update my derivative to make sure that it matches the function that I'm inputting. So for instance, I'm going to go over and navigate over to the denominator here. So instead of d dx, I'm going to delete the x and create the variable alpha 6 to do t. Now I'm doing the derivative with respect to t instead of x. Now I can input my x and t key, just using t's however much you want, or you can use your var key to grab a predefined function. I'll grab my dx of t function. Again, my x and t key now defaults to t because now that's what the derivative is in terms of, and I can input the t value that I want to take the derivative at. For integrals, let's go into the toolbox and navigate down to integral. First, I'm going to input the bound, so I'll do 0 to 8. And now to change the variable in which my integral is done in, I'm going to navigate to the end of the integral and then back into the dx part, clear out the x, and add my t here. And now my x and t key will be t instead of x. I can also, again, grab the predefined function in the var key and then input dx of t. And I'm taking an integral here with respect to the t-axis and not the x-axis. Let's take a look at the 2018 AP Calculus AB free response question. Question 2 says, a particle is moving along the x-axis with the given velocity v of t for the time 0 to 3.5. The particle is at a position of x equals -5 at t equals 0. Find the acceleration of the particle at time t equals 3. Let's start by inputting my v of t function in my calculation app. I'm opening up the calculator, and I'm going to store this function 10 sine of 0.4 t squared over t squared minus t plus 3. And I'm going to store this as my v of t. Question A asks us to find the acceleration of the particle. We know that the acceleration of the particle is equivalent to the derivative of the velocity. So I'm going to take the derivative of the velocity equation that we just created. So I'm going to go into my toolbox and grab the derivative. I'm doing this with respect to t, so I'm going to change my terms of my derivative to t. I'm going to use my variable key to grab my v of t function. Also worth mentioning, if you have other functions here from previous problems, you can delete these directly from the variable box. So I'm going to grab this v of t, and we're evaluating the acceleration at t equals 3. So a of t, a of 3, is equivalent to negative 2.118. Let's take a look at part B. Question B says find the position of the particle at time t. To find the position of the particle, we need to find the accumulation of the velocity from 0 to 3 plus the original position at x of 0. And this will give me my x of 3. X of 0 we know, well, when time was 0, the x position was at negative 5, so that's going to be negative 5. So let's compute that. I'm going to use my toolbox, grab an integral from 0 to 3. I'm going to change my integral so that it's in terms of t. Use my var to grab my v of t, and we're going to subtract 5. This will give me my x of 3 value, the particle's position at time 3. Let's look at part C. Part C asks us to evaluate the integral of v of t from 0 to 3.5 and the integral of the absolute value of v of t from 0 to 3.5. Interpret the meaning of each integral in the context of the problem. Okay, so I just need to do a variation on the integral that I just computed. So I'm going to click up and over and press OK to copy that integral. So the first thing I'm going to do is 0 to 3.5 on v of t dt. I'm going to clear out by minus 5. And in my upper bound, I'm going to edit the upper bound to be 3.5. Now to compute the same integral, but instead of v of t, we're doing the absolute value on v of t. I'm going to click up and over and press OK to copy the integral from before. I'm going to navigate inside my integral until I am before my function, and then I'm going to use my toolbox to create the absolute value. I'm going to open my toolbox, I'm going to back out of the calculus section, and I'm going to navigate up to the absolute value operation and press OK. This will create the absolute value bars around the v of t function and press OK. Now that I have my two calculations, I'm going to move my calculator out of the way. And they ask us to interpret the meaning of each integral in the context of the problem. So the first integral is calculating the displacement of the particle at the time 3.5. So at t equals 3.5, the particle is 2.844 units to the right of the position at time 0. On the other hand, when I added the absolute value around the v of t, what I'm calculating is the total distance. So the particle has traveled a total distance of 3.737 units from t equals 0 to t equals 3.5. The next application we're going to take a look at is the equation application. I'm going to navigate over and open up the equations. The equation solver is great for those derivative and integral equations that you're asked to solve. For example, I can open up my toolbox here and I can grab a derivative function. So here I'm going to grab the derivative. I'll use one of my predefined functions in my var key. So I'll do the derivative of f of x. I'll take this derivative at the variable x. So what I've now just created is the derivative of f of x at x. And I can set this equal to 0. So I can do shift pi, setting this equal to 0. This is going to find when my first derivative is 0. In other words, I'm finding all of my critical points. I can go down to solve the equation. I can tell it the interval that I'm interested in. So for the moment, I'm interested in -10 to 10. You can edit those if you want, and you can solve the equation. I can also back up and edit my function. So currently I've done the first derivative of my f of x function. I can quickly create the second derivative of the f of x function by adding a square onto my d dx, and now I'm taking the second derivative of f of x with respect to x, setting it equal to 0. This is great for finding your inflection points. And again, you'll want to give it a min and a max, and it can solve the equation. These x values are the x values where the second derivative of my f of x function is equal to 0. The last part of question 2 from the 2018 exam is part D. A second particle moves along the x-axis with this position. At what time are the two particles moving at the same velocity? Here we're trying to determine when will the second velocity, v2 of t, be equivalent to our original velocity. When are the two particles the same velocity? So the first thing I want to note is what is v2 of t. This is going to be the derivative of my x2 of t. So I can quickly take this derivative. You can use my power rule to get 2x minus 1. So now the equation that I need to solve is when is 2t minus 1 equivalent to v of t. Let's open up my calculator and go into the equation to solve this. I'm going to input my equation. 2 alpha t minus 1 is equal shift pi, and I'll go into my var key to grab my v of t. Now that I have my equation typed in, I'll go down to solve the equation. My bounds here is I'm only really interested in the solutions between 0 and 3.5. So I can solve for the t when this is true. The last application we'll do a quick little look into is our sequence application. This is great for your BC calculus courses where you have to study the convergence of sequences. Let's press OK on sequence. In the sequence application, I can look at a sequence of partial sums, and this will help me to determine whether series are convergent or divergent. Let's take a look. To add a sequence, I'm going to use my toolbox key and grab my sum calculus feature. Here I'm going to input the lower bound of my series. So I'll start at k equals 1, and I'm going to go to n. Again, I'm creating a sequence here of partial sums. Now inside my sum, I'll put my sequence. So I'll do 1 over. Because the sum is in terms of k, my x and t key here will default to k. And I'll do a p series where the p value is 2 and press OK. Now I have a sequence of partial sums, and this is going to help to determine if the series converges or diverges. One way I can do this is I can navigate down to plot the graph. This is a great visual to see if the partial sum has a limit. I can also explore this in the table of values as well, where I can see, does the sums converge? And I can input values, large values, to see if they come to a converging value. Let's take a look at how we can use Euler's method in our sequence application to approximate a solution to a differential equation. In our problem that we're given, we're going to let dy dx equal the square root of x times y. We're also given that the initial value of y of 1 is 4. Use Euler's method with a step size of 0.25 to estimate y when x is 2. So the first thing that I'm going to do is I'm going to set up a table of values for x and y. First thing to understand is that Euler's method is a sequence. You're given an initial value of x. In this case, my initial value of x is 1, and we're asked to create a sequence of a step size of 0.25. So we're going to create the sequence by adding 0.25 to each x value. Let's talk about how we can use our sequence application to create this sequence. I'm going to open up my calculator and go into the sequence application. I'm going to add a sequence, and I'm going to make this a recursive first-order sequence. I'm going to start by saying I'm going to take the previous value, u of n, and I'm going to add to that my step size. I'm going to start my sequence at the value 1. Now what you'll see when you display the values, you'll see for each step size the appropriate x value in your u of n column. Now let's talk about how we can take a sequence of the y values. Let's navigate back up to our sequence and press OK. I'm going to add another sequence, and this sequence is going to represent the y values, and again, I will do another recursive first-order sequence. To understand how we need to create the sequence of y's, we first need to understand how we approximate our y values using Euler's method. To approximate y, we're going to take our previous y value. We're going to add to that the slope times the step size. So here my slope is the square root of the previous x value. Again, I'm just getting this slope from my dy dx, but again, I'm doing the previous values. And then I'm going to multiply the slope by my change in x, or in this case, delta x, which is 0.25. Okay, let's define our sequence. So v is my y, so I'm going to do my previous y value plus the square root of my u of n values. Again, u here is representing x. I'm going to go into my toolbox and grab u of n. I'm also going to multiply this by my previous y value. In my toolbox, I can grab v of n, which represents my y's. And then again, I'm going to multiply this by my step size. I do need to give my y's a starting value, and we were told originally that when x is 1, y is 4. So now I have a sequence that represents both my x and my y values. I'm going to navigate down to display values, and I don't really care about all my y values, but what I do care about is that when x is 2, I'm interested in the estimate of the y values. So here the estimate of the y values when x is 2 is 11.12. Thank you so much for joining me, and good luck on your exams.